everyone, and thank you for your time. I know schedules are very busy right now, so we are glad that you joined us. We're really excited about the content that we'll be sharing today. And really throughout the discussion, we'll be covering how healthy building technology can help you future-proof your schools by reducing the risk of illness while also reducing costs. My name is Brooke Vanderland. I'm on the marketing team here at R0, and I'll have the pleasure of introducing our experts. We'll spend some time really just setting the stage around the national attention that indoor air quality is getting, all the data that's readily available on its impact on student health and performance, and really make the case that healthy indoor spaces are no longer a nice to have, but a must. We'll talk through some proven solutions of meeting that need, and the meat of our discussion will be spent going through a real world study that we're super excited to share from one of the 5 largest school districts in the country. With that, I will pass things over to Olivia to introduce herself, and our distinguished speakers. Excited to pass the baton over to you all.
Thanks so much, Brooke. Hi, everyone. Thank you so much for joining. Good morning, good afternoon, wherever you're based. My name is Olivia Cvitanic. I'm a senior account executive at R0. I cover the West Coast, and my background is in public health.
Great. Hi, everyone. My name is Koutras. I'm a biomedical scientist, and I lead our science program here at R0. And my focus is validation of the safety and efficacy of health technologies. So that's what we'll be talking about today. All right. In the last 3 years, if there's anything at all that we learned, is that the air we breathe really matters. And that's not surprising, since the average person spends over 90% of their time indoors. And when we think about educational settings and this idea of spending time indoors and indoor air quality, what it really means is that something as simple as ventilation actually can play a major role in student success. We know from a number of studies looking at classrooms with poor ventilation versus classrooms with good ventilation, that students in well-ventilated classrooms can achieve higher scores, up to 15% in the standardized tests in math and reading. We also know from the pandemic that spending time in classrooms where there may be other students with COVID-19 can make people sick. Sending kids home is not necessarily going to be the best option. I mean, school closures will happen, but if you send kids home, then there's a problem with the digital divide, and not all kids will have access to computer or a good nurturing learning environment. So that can also impact their scores. So poor IAQ, whether it's particulate, it's biological contaminants, poor ventilation, will impact the student performance and health. And when we think of COVID-19, it's not the only virus that can be disruptive of schools. Flu and RSV have been around for a long time too, and we know that they can be a concern. And they underscore this aspect of indoor air quality, that is the presence of biological contaminants. So people will get sick when they breathe indoor air that is contaminated with pathogens, viral or bacterial. And the contaminated air that has enough of these viral bacterial particles is really what we call this infectious dose, which will depend obviously on how contagious a pathogen is and our own immune systems. But the link is very clear. If you spend more time in an environment where you have a large concentration and exposure to microbes, then your risk of getting sick is higher. Right, thanks. Slide. The scientists have actually studied that very well during COVID-19. In Italy is a very interesting country where most schools don't actually have good mechanical ventilation. So a lot of schools, they just open the windows to let air in. Some schools do. So what scientists did is that they look at schools without mechanical ventilation and then looked at schools with mechanical ventilation and what is the effect of introducing 1 ACH, 2 ACHs, 4 ACHs, and 6 ACHs. And what they found is that, in fact, when you add more air exchanges, you can decrease the infection rates by over 80% in that environment. So in the next slide. So this is really just underscoring the fact that virtually every health agency, scientist, and government recognizes that ventilation and having good indoor air quality can really keep people safe. The CDC, they have a number of guidelines, and they developed more guidelines during COVID-19 for schools, talking about what they can do to improve ventilation. In March of last year, the government, the US government, they launched what we call the Clean Air in Buildings Challenge, and that's to help building owners and operators improve indoor ventilation. And more recently, California passed new law in December. The White House announced that all federal buildings, that's over 1,500 buildings in total, would have to meet minimum air safety requirements. And finally, just a couple months ago, ASHRAE, which is the American Society of Heating, Refrigerating, and Air Conditioning Engineers, they announced that they are working on an expedited timeline release of a new standard for indoor pathogen mitigation that is going to be code enforceable. And I actually have the honor of being part of that committee. So, and that's also happening in the UK and in Belgium and other countries. So in the beginning of the pandemic, we used to talk about new technology is coming for us. And now we're past that, and it's really code is coming for us. So I'm excited to have Olivia talk a little bit more about what we can do to help mitigate poor indoor air quality.
Sure. Thanks, Carolina. Yeah, so piggybacking off what Carolina said, so if the foremost experts on air quality and environmental safety are all in agreement, then how did we get here? And I think it's worth discussing. So, well, it's largely because many indoor spaces, and especially schools, are chronically underventilated from a human health perspective. So now we've seen the impact of that with COVID. The priority for most buildings up to now, or at least in recent years, has been energy efficiency. And that has often led to sealing off buildings to reduce the energy required to heat or to cool them. So while these indoor environments are energy efficient, they fail to address a critical area of occupant health, which is basically, we want to improve the situation so they don't become ideal spaces for exposure risk if someone comes into your space sick. So to that end, most buildings currently rely heavily, if not exclusively, on their HVAC systems for circulation of air. HVAC systems were designed primarily for thermal comfort, not for human health. So when someone is sick in a shared space and actively shedding virus, like we saw in COVID, the likelihood that someone else will get exposed to an infectious dose of air, as Carolina described before, if the air in the room only turns over every 30 minutes and not 2 air changes per hour is pretty common in a school environment, that makes that likelihood of exposure quite high. So achieving the recommended air changes per hour to reduce exposure risk typically requires more labor, and it's a cost-intensive upgrade. And also HVAC is a really limited tool, and that you can't target specific rooms that have a higher risk profile. So for example, you can't provide more air changes per hour specifically in a high risk space like a cafeteria compared to maybe an individual office nearby. It only has, HVAC usually just has one setting for an entire building. So the main thrust is then, how do we close the gap between existing and recommended ventilation rates defined here? So next slide, thank you. So traditionally, these have been the 3 methods for improving ventilation and lowering exposure risk, but they each present real limitations in schools. So the first one is natural ventilation, i.e. opening your windows and doors. The issue with that is that it's not always feasible at all times during the year, especially depending where your school is located. Like if you're in the Northeast, it's way too cold at times of the year. But it also means it's inconsistent air turnover and permeability into the room. So that person that's sitting right next to the window might be reaping great benefit, but that cluster of students, in the farthest corner away from that open window or door may be getting very little benefit in terms of fresh air exchange. HVAC, which we already kind of touched on, but the primary focus is to heat and cool large volumes of outdoor air, which takes a lot of energy to do in addition to the energy required to mechanically turn over those large volumes of air. So heating and cooling it and turning over large volumes of air is energy intensive. HVAC on average accounts for 35% of commercial energy use. So increasing the air changes per hour through HVAC just means higher energy costs and greenhouse gas emissions. And usually that counters any kind of sustainability or decarbonization goals that your district might have. So last but not least, too, HVAC systems remove microorganisms by extraction, not inactivation. So for example, just to kind of provide some sort of rough visual with my pantomime, if someone is in a room shedding virus and they're in one part of it, yes, once that air travels potentially across a room of people and goes into the HVAC intake, great, it has left the room. But unfortunately, that doesn't do much for the people in the room where they're actually could be breathing in that infectious dose of air. So having the solution in room, which we'll talk about later, is better from a mitigation perspective. And then the third kind of one that we've seen is in-room HEPA. The issue is that there's limited efficacy for the same reason as HVAC. It requires that potentially infectious air to cross the room over to the HEPA filter. Again, it's a really appropriate solution if you want to take out particulate matter, so dander, pollen, allergens, but it's not as appropriate for taking out something as small as viral particles, which are at the micron level. They also require usually more maintenance to change out the filters on a regular basis and deal with biohazardous material. Next slide, please. So what do we want to make clear about offering is the upper room UVGI systems and the far UVC that we offer and that are different. So you can kind of see here, I think you're going to get an animation that they're kind of visual. But basically, what we offer is an upper room UVGI system and far UVC, but the upper room UVGI is going to put out UVC over the top of the room. So it's coming above head height. And as we breathe, cough, talk, respire, whatever it may be, we're expelling air that's warmer than our core body temperature. And as a result of that, it rises, and usually quite quickly. And as it comes in contact with that beam of UVC over the top of our heads, it's disinfected. And as that air cools, it's recirculated back into the room. So essentially what you're getting is real-time disinfection cycles happening in the room where infection typically, or at least transmission, is typically occurring. On average, a beam is going to deliver, so beam is our upper room UVGI device that's doing that. We deliver on average 12 equivalent air changes per hour in a room. So that's the number of times that potentially infected air is changed over with disinfected air every hour. So in essence, you're turning over potentially infected air in a room every 5 minutes. And that's really powerful when you talk about mitigating the likelihood of exposure in a space, especially compared to turning over the room every 30 minutes. And last but not least, we've got far UVC, the Vive. So I think it's right. Brooke, I don't know if you can point to it, or I guess we've got kind of the arrow. But it emits far UVC, and it comes down in this kind of cone of disinfection. So that's going to disinfect surfaces and air simultaneously. So the benefit is we kind of put it over, like in this case, we're putting it over a food station where you're not just concerned about people sharing air, but there's also these common high-touch surfaces. The kind of unique thing about UVC, this far UVC, is that you can have direct exposure to it. It emits UVC at a 222 nanometer wavelength, and it doesn't penetrate that top layer of your skin, your stratum corneum, or the tear layer of your eye, which can cause irritation with traditional UVC. But both products have been tested at independent EPA accredited laboratories to demonstrate efficacy against common and difficult to inactivate viruses and pathogens. So for most schools, Beam and Vive provide effective and continuous air and surface disinfection in occupied spaces with zero additional labor required, without any distracting noise, and they can be deployed in any climate. Also, I think it's worth noting that both devices are equipped with heat and motion sensors. So they turn on when that's sensed in combination, i.e. a person entering a room. They're also enabled to feed that data of when disinfection cycles run to a central dashboard and for how long those cycles ran. So you suddenly get all of this visibility into when disinfection is happening in your spaces in real time, which is definitely a standout compared to previous methods where maybe somebody's checking their name on a clipboard, or you have to take their word for it that a room has been disinfected or cleaned in some way. Next slide. We've already kind of touched on this, but basically we have quantified the difference in energy consumption to deliver an equivalent air change with beam and vibe compared to trying to deliver an air change mechanically with HVAC. With that delta being about, go back real quick, Brooke, sorry, with being about 95% less energy to deliver that air change with a beam or vibe. So our climate and energy data that we did to compile these statistics is based on modeling done by an independent third party who looked at this across 6 major cities in the US. So we can get more into this later if that's interesting, but it offers a way to help achieve better disinfection in your schools, lower the likelihood of exposure while providing a safer indoor environment and helping you meet any sustainability goals. Next slide. So we often get the question, so like, how do you do this? What does this look like? And I felt like it was worth including here, but this is pulled from an actual anonymized proposal that we did for a school. So we do risk modeling space by space to look at what is the likelihood that if someone enters this space with SARS-CoV-2 or COVID Omicron variant, that they will expose at least one other person based on how the room is used. We use COVID because it's still, unfortunately, an issue and top of mind for a lot of school districts and our other customers. But also, we know that if we're having this kind of mitigation effect against COVID, which is so transmissible, it absolutely holds for other common pathogens. So common cold, influenza, RSV, and other things that kind of routinely put us out of the office or out of school. Further on this, just to kind of touch on this really quick and what this means. What we're saying here is in this average classroom, so these inputs about occupancy, room size, modeling behaviors, which is sitting without mask, those are all generated from the customer that we put into a machine learning algorithm that takes a pathogen and it knows how infectious it is and ranks it then and manages how likely it is that a person will be exposed. So just explain that. So all these inputs are coming from customers, and we're saying here that as it stands, based on these dimensions, an 800 square foot room, 30 permanent occupants for 3 hours, that likelihood of exposure is approaching 37%. And deploying a beam here in this room, so that upper room UVGI, putting the beam over the top of the room, reduces that likelihood of exposure to 8.6. So again, we modeled this space by space as part of a proposal that we put together. We have one more cafeteria, Brooke, if you don't mind switching, just to show. Again, this is for the same school. They had 100 transient occupants per hour eating lunch. Let me go back one real quick, Brooke. But basically saying, you know, we've got beam and vibes, and this is how we deploy them. We put vibes, again, over their food station areas that are super high touch, and then beams to cover the air disinfection continually when the space is occupied and when students came in to eat lunch or do kind of an early breakfast program that they had there. So again, some spaces carry a lot higher risk. This is a 62.3% infection risk. We were able to bring it down to 20. Brooke, go one last slide here. Also too, I think this is very important. We recognize that budget is always a factor. So what we do actually, once we take this data and we've risk modeled it space by space, looking at your likelihood of exposure, we stack rank it based on high, medium, and low risk spaces so that you can then make the most informed decision about where we want to basically deploy devices to get the biggest bang for our buck and then meaningfully reduce risk as much overall in our building or facility or school district. And that's it for me.
Great. And so now we'll be talking a little bit more about the study that we did to validate this device. Again, UVC technology has been around for a long time, but the beam, this upper room UVGI fixture, is a newer technology. It uses LED lights and it has a number of safety sensors, actually won a design award. So we wanted to validate our own device in the real world. We're very, very lucky to have an opportunity to partner with Dr. Edward Nardell from Harvard. For anyone who's been researching this space and learning more about upper room UVGI, he's the most prominent researcher in the field. He's globally known for his work in infectious disease, as well as validating a number of different technologies to to mitigate the spread of infection. And Dr. Edward Nardell partnered with Dr. Edwin O from the University of Nevada. Dr. Edwin O, he runs one of the largest wastewater research programs in the nation. So very lucky to partner with both of them to study and validate this device in the real world. So we could reconcile the data that we have from lab studies that show that it works against SARS-CoV-2 and other microorganisms. We can't name the school district. Obviously, schools have students. It's a vulnerable population, so we're very respectful, and we're not naming the school district, but it was a very large school district. The study was approved by their research office. And in addition to the research team, Dr. Nardell and Dr. Edwin O, the school district did assign a sponsor who was a stakeholder from the schools. And this person essentially was an individual who oversaw the facilities, was an expert in IAQ and also microbiology, and she cared deeply about student well-being. So we worked with her as we're implementing these devices. And R0 was very arm's length, so we really just donated the product. The study was independently designed by the research team. And so what we did is that we had 8 schools. They were paired according to social demographics as well as school infrastructure. And we have a group of 4 control schools and a group of 4 intervention schools. In the end, we had to remove one school because we were using wastewater to look at the efficacy of the device. And I'll talk about that just a little bit in a second. Simply because when you're collecting wastewater, you have to make sure that the building is not having any cross-contamination from any other nearby buildings. But we still had a very large sample size of just under 5,000 students and staff in total for the study, which was excellent. So we did use wastewater for the study. It's not possible to study SARS-CoV-2 to perform tests on all students and staff. That's something that wouldn't just be feasible. But the advantages of wastewater are many. It's already used in our public health system, and it also allows us to look at both symptomatic and asymptomatic individuals altogether. So what the researchers did, these were elementary schools, and it turns out that we know the behavior of these students. So in elementary schools, apparently they use the facilities at lunchtime. So what they did is that they went 3 times a week in every school and collected wastewater samples around lunchtime. And those samples were sent to the lab and analyzed for SARS-CoV-2 presence and quantified. Obviously, just giving you an overview here, this is a study that was heavily controlled just to make sure that any fluctuation in population from schools would not impact the results. And so when they look at differences between control and intervention, we're really comparing apples to apples. Next slide, please. And so what the researchers found was that there was a 53% reduction in SARS-CoV-2 levels in the intervention schools compared to control schools. So what they noticed is that when they taken the samples, there were fewer positive samples in the intervention schools after this treatment was deployed from January all the way through the end of the semester, end of May last year. And not only there were fewer positive samples, when they quantified, there was significantly less, so a 53% reduction in SARS-CoV-2. And so this study, as you think of January through May of last year, it was right at the high of the Omicron wave. And in fact, the study started 2 weeks after the county where these schools are located had over 2,000 cases of COVID-19 a single day. So it was really good timing to study this. Obviously, it's an school environment. Schools are incredibly difficult to study, especially for these epidemiological studies, because obviously, as you could imagine, kids will be, they can get COVID in extracurricular activities, in the school bus, in other settings, and they will bring that to school. But what the study really showed here is that you actually can significantly lower the levels of virus in that environment, suggesting that the students in the intervention schools were less at risk of contracting SARS-CoV-2 during the school semester. Another interesting finding was that there were 0 safety incidents. Although I said interesting finding, we're not hoping to see anything because, like I said before, this is a device that is designed with safety in mind. So it has all sorts of motion sensors, which you would not find. There is no other fixture like this device on the market. So when it shines the light in the upper part of the room, you could imagine an accident if someone were to, climb up or try to change a light bulb. That will never happen with this device because of motion sensors. It would immediately turn the lights off. So we saw 0 incidents. And the nice thing, too, is that we didn't see any complaints from parents or staff. And that's something that could have happened just because it's UVC, and it's normal that there would be potentially concerns about, safety and that no one is getting exposed. So no complaints, no safety incidents. Very relevant because this is an environment, like I said, people will bring in infection. These were not boarding schools. But the nice thing is that even though we researched SARS-CoV-2, upper room UVGI and any other UVC technology, it's not as specific to a pathogen. It's not SARS specific. They really the light will target DNA and RNA, and that's how the light inactivates microorganisms. So this technology worked well for SARS-CoV-2 and will work just as well for any other respiratory virus in that environment. And all of that was without any additional labor. So these are completely autonomous technologies. So once you install them, they're there. You can just program them on the computer using the dashboard, and they will just be running during school hours. And when there's no one in the room, when the fixtures don't detect anyone in the room for a few minutes, they will just turn the lights off. So again, very good for energy savings. And you just really don't need any additional labor for these fixtures. Next slide, please. And so here, just very quickly, I just want to go back on this fact that even though we run a study, because we feel that we have the best upper room UVGI that was ever developed in terms of safety and efficacy, upper room UVGI is proven technology. First of all, UVC won a Nobel Prize in 1903. So that's a very long time ago when Dr. Finsen, who was a Danish physician, he used UVC light on tuberculosis lesions to treat that. And then ever since, there are a number of studies in schools as well as healthcare environments showing that upper room UVGI fixtures can stop the spread of microorganisms, including tuberculosis bacteria, as well as measles. Measles is one of the most contagious viruses out there, and that can be extremely effective. And so here you have a picture of what the very old fixtures looked like in the 30s when they did those studies. So this is proven technology, and we're very excited about these results. Dr. Nordell is presenting them at one of the largest conferences in May. It's the ATS conference, and they're also finalizing a peer-reviewed manuscript.
So essentially, we've all experienced the challenges and difficulties of remote learning through COVID. That's very apparent. But while we are inspired to fight against COVID, the products and expertise we developed applied beyond COVID to help kids stay safe in school through a variety of outbreaks. Most recently, that's been RSV, but on a continuous basis, we see flu, common cold, stomach bugs always becoming an issue and resulting in absences. And then in turn, over time, differences in learning and ability to achieve, I guess. And student scores. So we want schools' preferred long-term partner to be us in helping their students achieve their highest potential by future-proofing their classrooms and helping keep students and staff safely in school in perpetuity. And these are some of our partners, just to be clear. So again, in the public or in the K through 12 space, hopefully some of these names are familiar, and we may actually have some folks from these districts on this call. So if you're one of those people, thank you for joining this webinar.
Awesome. Thank you, Olivia. We have quite a few questions that continue to come in, so I'll just start feeding them over to you guys. I know we touched on this a bit, but one question that came in kind of pre-submitted is, what is a typical prescription for a school? Do I have to implement this in every room?
Carolina, do you want me to start on that one?
Yes, go ahead.
Yeah, so kind of like we outlined in the risk modeling before, and when we stack rank, like cafeterias versus individual offices versus a classroom, we will help you to determine basically what spaces present the most risk. So no, the answer is you don't need to outfit every space for it to be effective. Even in the study that Carolina just presented that we did, it wasn't in every single room. It wasn't in every single restroom and every single cafeteria. That wasn't the case. But we just tried to pinpoint the areas essentially where you can holistically lower your risk the most by putting it in the spaces that present the highest likelihood of exposure. And we work with schools on an individual basis for that. But we know now, having done this for quite some time, that certain rooms, locker rooms, cafeterias, for example, are definitely where you want to prioritize putting devices to lower your risk. So, and again, we work with you on that individually.
Awesome. A specific question came in from Colin. In his area, many schools have unit ventilators below the windows. Does this affect the efficacy of UVGI at all?
Carolina, do you want to start on that, or do you want me to take it?
Go ahead, Olivia. Sorry, I was just answering to a question in the chat here.
So the question again was, if schools have unit ventilators below the windows, does it affect the efficacy of UVGI at all?
Oh,
no. Yeah, go ahead, Carolina, go ahead.
No, actually, UVGI works well through what Olivia explained. So once you exhale warm air, it will naturally raise, and then it will get disinfected. And then as it cools down, it lowers. But actually, if you do have some air mixing, that actually is better. It improves the air circulation. And so we will have more passes, and microorganisms will be disinfected through the disinfection zone. So that is not an issue.
Awesome.
Brooke, do you want me to take Daryl's question, just going up the list here?
Sure, yeah, and I think Aaron's are good as well. We have quite a few, but why don't we just start knocking them out?
Okay. Awesome. Thank you, everybody, for writing in. That's amazing. We love to see that. So Daryl, Daryl's question is, who within the school district is the decision maker? So typically it's a conversation that started with your chief of facilities, whoever that may be, and the superintendent. And kind of making sure this aligns with their goals and looking at costs and all of that. And then typically then it will go to a board vote is what we've seen. Fortunately, and I think it's worth mentioning, a lot of the ESSER funds or any kind of COVID related funding, we fit squarely into that tranche in terms of being eligible. So if you have any funds that are going to expire, most public schools have used that funding specifically to pay for this technology.
Awesome. A few questions have come in from Aaron, and I'm not sure specifically, we can maybe talk about both of our devices, but just, general commentary on energy consumption of the devices, either in wattage or, just a typical comparison of how much energy that it would draw. And then talking about the expected life of the lamps, what is their necessary lamp replacement, and what maintenance look like.
Yeah, so lamp life for Vive is 5,000 hours, and for Beam, it's 10,000 hours. So we're seeing in reality for Vive, our power users are actually having to replace those maybe every 1 to 2 years, and Beam, it's every 2 to 3 years typically. And that replacement process is covered within your warranty with us, essentially. Also, just to give you a specific wattage, Aaron, typical power consumption for a Beam is 160 watts or 2 amps. So it's really minimal power draw. For Vive, that is 60 watts on average. So hopefully that's helpful. But again, it's intentionally very minimal.
Awesome. Thank you. Yeah. And on that note, we also have a question about any validation around Vive's efficacy.
Yes, great question. We do have quite a few lab studies, and we also have a real-world study. So we just finished concluding a study at Mayo Clinic, and we're excited to have that publication out. We didn't present it here today, but we do have data on Vive, and happy to follow up offline and provide more on that.
Awesome. Any commentary on how this technology compares to bipolar ionization?
Yeah, Caroline, I'll let you get into the specifics, but basically at a high level, we haven't seen the same kind of well-studied efficacy around bipolar ionization. Like if your school adopted that, like that's understandable, especially at the beginning of the pandemic. I mean, that was the time when we were still Lysoling all of our groceries because we really didn't have that much information about how it spread. But now that we know more about how COVID, but other things are transmitted through the air primarily, we're just trying to provide better, really well-studied, highly efficacious solutions to address that. And we just haven't seen bipolar ionization achieve that really consistently in any kind of third-party peer-reviewed studies.
Yeah, that is correct. That's what I would note is the UVC and upper room UVGI. It has been around for a very long time. So there's a ton of data and there's still a lot of discussion around the efficacy of bipolar ionization.
Awesome. Thank you both. How do you show to your customers that your solutions are effectively working? We talked obviously about that in our presentation, but any other commentary just around how to prove that it works?
Carolina, do you want to start that one?
Yeah, so we'll just touch briefly on the studies. So we are compliant with EPA. So all of our efficacy claims are heavily substantiated. We have the largest efficacy testing profile for all of our products than any other company selling UVC products. So we do have studies, we have real-world studies, we have references from customers as well, and we can provide all of that data. We're very familiar working with school districts. Sometimes when they have to build the business case, they actually will bring in our science team and we can present those studies. But other than that, it's well validated already. So we have all the data to back up the efficacy. Olivia, perhaps you want to touch a little bit on the dashboard and what can help schools track the devices are working and are benefiting that environment as well.
Yeah, so basically, like we kind of touched on, when all the devices run a cycle in a room, that is immediately logged into a dashboard. And then you can see when those disinfection cycles have run in real time. And we know how much UVC is being output. We do all of that during the install and safety commissioning process. And UVC is such an old technology that we know the dose to the specific pathogen in question that is required to inactivate it, or to make it, render it harmless, I guess, for a less scientific kind of term, but basically to get rid of it in your space so it's not harmful. So because we know that, we know the dose delivered, it's really easy for us to say, yep, we're delivering an effective dose of UVC in your room every time this is run, to deactivate all of these harmful organisms. And we really focus on for a school environment, RSV, common cold, influenza, norovirus, and of course, COVID. So those, because they account for the majority of absences. A little bit of a different pathogen, simply, but point being, we know the dose delivered, we know the inactivation rates because it's such an old technology and well-studied. So, and we know when you're delivering those cycles in a room because it's feeding to the dashboard and you can tell when they're on. You can see they've got the lights on them. So all of that in combination hopefully can provide some reassurance that like this disinfection is happening in real time in my classroom, in my cafeteria, or wherever.
Awesome. Thank you all so much for... Oh, go ahead, Carolina.
I was just going to say, obviously you can see it. And so it does provide another level of, just validation check, knowing that it's working. And if anything were to be wrong, then you would just get an alert to see what's going on. But usually they're fairly easy and autonomous and they are always on.
Yeah. It's for what it's worth too, in specialized cases, like obviously in addition to this, like intensive study that we did with Harvard at a top 5 school district, we sometimes rely on dosimeter cards. So these are, you can buy them online, but they just measure the amount of UVC dose you're delivering in a space. So sometimes we'll do that at commissioning to make sure, okay, we're meeting the dosage that we say we're meeting. And then also too, we have bioindicators. And again, Caroline, I won't get into all of that. But basically, we do this a lot with our healthcare clients because obviously that is an extremely important metric to hit with them. But we have tubes basically that have UVC translucent film around them or plastic around them. And when it goes through that, we can show, because there's a known amount of bacteria or viral load in there, we can show that that's inactivated in a space. So again, it's not something we're doing routinely, but certainly in healthcare, those are some additional metrics that we provide.
Awesome. Well, we have one last question. Thank you again for everybody in your engagement and submitting questions. The last one is, what are cost-effective ways of improving older buildings ventilation? Can you list the low-hanging fruit? So I know we touched on that a little bit, but just highlighting that, anything specific to older buildings.
Yeah, I'll jump on that, because that's kind of our sweet spot in terms of who we're trying to help, who say, look, we're tasked with getting these ventilation rates up in some way to keep our students safe or our staff safe, but it's really difficult. Older buildings tend to be poorly ventilated, but also sometimes it's just not feasible to do the HVAC upgrades or retrofits you need to try to, even put a MERV 13 filter on it or increase your air changes per hour. So in that sense, where we're deploying something in room that doesn't require any HVAC upgrades to get better disinfection and reduce your likelihood of exposure, that's exactly where we plug in. We're complementary to your HVAC system, but we're especially critical when doing an HVAC upgrade. It's untenable anyway. And it's a lot more cost effective, even for spaces that have an HVAC that can be upgraded. For the reasons we talked about, it's a lot more cost effective to try to achieve that through our devices than trying to crank up your HVAC.
Amazing. Well, we are nearing the end of our time. So, want to just say thank you again to everybody who has joined us. And, as Olivia said, we really are here to help and here to learn about, your needs in your space and see if there's a solution that makes sense for you.
Thank you so much.
Thank you, everyone.